Hey everyone, I'm just going to give a short video on how to do some specific heat calculations. I'm going to use some questions from STAWA as the example. So the first one I'm going to use is number 3.7, where you have been given the energy, you've been given the mass, you've been given the temperature change, and it's asking to find the specific heat capacity of the steel. So I'm going to use the equation Q equals mc delta T as a starting point. I've been given the mass as 286. I need to find C, that's what I'm looking for. The change in temperature is going to be 452 take 22. That's going to end up being 430, and that's going to be equal to the 55.3 times 10 to the 6 because it's megajoules. I'm going to rearrange that. I'm going to get C is equal to 55.3 times 10 to the 6. I'm going to divide it by 286, and that's 430. And when I put that in my calculator, I'm going to get 449.7, three significant figures, so 450 joules per kilogram Kelvin. So that's your standard calculation for any sort of specific heat determination. What I'm going to do now is move on to when you have heat that's transferring between two objects. We've got some soup that's going into a bowl. So if I was to sort of draw that as a diagram, I could say that this is my bowl here, and then I'm going to pour some soup over the top. And what's going to happen is there's going to be a heat transfer from the hot soup into the bowl. So first I need to state a really clear assumption, and that is that the Q lost by the soup, or the heat lost by the soup, is going to be equal to the heat gained by the bowl. Now, what's interesting is I've put a negative sign here. I'm not sure if you can see it, but that what that's telling me is that one is going to be the negative of the other. And that might seem a little bit counterintuitive, but if I expand that out, I'm going to have mc delta T here for the soup. And that's going to equal to negative mc delta T for the bowl. Now, if we have a look at the heat lost by the soup, the change in temperature is going to be a positive number. The delta T on this side is going to be a little number because it's going from 10 degrees and then it goes up to 97. So that's going to be a negative value. So you notice that that delta T being a negative cancels out that negative sign at the front. So sometimes you'll see in my working out, and you might even see it online, they really sometimes just erase the negatives to avoid confusion, so long as you make sure that this delta T and this delta T are both positive values. Otherwise you could end up in a bit of trouble. So from here, I'm just going to put in the numbers. I should get 0.8. C is what I'm trying to figure out. The change in temperature for the soup is 1 degree because it's gone from 98 to 97. And on this side, I've got my 0.1, my 320, and my 87. Okay, and then I rearrange that to get C by itself, and I end up with something that looks like this over 0.8. And you should get is 3,480 joules per kilogram Kelvin. Now, just a quick check on this. I'm quite happy with this number, mainly because it's close to the specific heat of water, and that's what I'd expect soup to be made of mostly. Okay, so let's make it a bit more complicated. So now we've got a mechanic that's adding some antifreeze to a radiator that's got water in it, which means that I have three systems interacting here, or one system interacting with two more. So let me just draw that up. So what I'm going to have is I'm going to have heat that's gained by the antifreeze, because the antifreeze, when it goes in there, is going to be at 22, so it's going to increase in temperature. Now, that is going to come from the Q lost by the water inside the radiator and the Q lost by the radiator itself. So I have basically the heat that's coming into the antifreeze is coming from both the water and the radiator. All three of them at the end of this will end up in thermal equilibrium, which means the final temperature is going to be the same. So just to sort of go a little bit further, I'm going to expand that out and put in mc delta T is equal to mc delta T plus mc delta T. Right, so now I've got the antifreeze, the water, and the radiator all represented there. I need to expand it further because I'm solving for TF. Now you could sort of work out delta T, I guess, but this is probably the easier way of doing it. I'm going to say MC, instead of delta T, I'm going to have TF take TI. Now in this case, the TF of the antifreeze is going to be larger than TI, so I know that's going to be a positive number. And on this side, what you'll notice immediately is that it's going to be TI take TF in order to produce that positive number. And that makes perfect sense. I should have the same thing on the other side. If I don't, then there's something wrong. Take TF. Right, so now I've expanded it out. I'm going to shift this across a little bit because you'll find out soon enough it's going to be pretty complicated. I'm now going to plug in the numbers for the antifreeze, the water, and the radiator. Now, the STAWA has this really annoying habit of asking you for information, like, for example, this ethylene glycol. That's given to you in the STAWA textbook in one of the other pages. I'm not sure if I have the number for that. The number it gives you is 2400 joules per kilogram Kelvin. And the radiator is made of copper. That's also given in the table that STAWA has, and that's 390. Now, those two bits of data are not given to you in the data sheet. So if this question was in a test, they would have to give you that information as part of the question. Anyway, so coming down here, I'm going to sub in those values, and it should look like this. I'm sure I'm going to speed this video up at this point. So notice that I've just put the unknown in there, which is the TF, and I'll do that with all of them. Okay, so let's have a look at what I've got here. I've got the antifreeze, so I'm using the mass and the specific heat of the antifreeze here, and then here I've got the mass and the antifreeze, sorry, the mass and the specific heat of the water, and the mass and the specific heat, and the temperature change over on the right hand side shows that it's going to be going down from 92 to something, and on the left hand side it's showing that it's going from 22 to whatever the final temperature is. So this is where it gets pretty annoying, really, is you now need to expand this out. So I'm going to do 0.655 times 2,400, and that's going to be, I've got it here, 1572 TF, right? And then I'm now going to expand it out, and I end up, if I multiply that value by 22, I end up minus 34584. Okay, so now I need to do that same thing with these two as well. So it's going to be a lot of terms, and they should look a bit like, I'll write them in now. Okay, so that's all expanded out, and you notice that each one of those expansions gives me a TF value and a non-TF value. So what I'm going to do to make things easier is I'm going to move all the TF values to the left, so all the values that have a TF to the left, and all the values that don't to the right. Okay, so now I've got all the TFs over here, so I've got TF, TF, TF. So now I can just put the TF on one side and then just add all these together and then divide. So once I do that, that algebra stuff that we all love so much, what I end up getting is TF is equal to 2791824. So that is essentially what these three add up to, and I'm going to divide it by what ends up being 31542, and I get a number that is 88.5 degrees Celsius. Now the important thing is that's a number that's less than the starting temperature, which was 92, which means it has cooled down the radiator, which is what I wanted it to do, but it's not like a ridiculous number like 3 degrees or 4 degrees or anything like that. So I can be pretty confident that I'm in with the chance with this value. This type of problem is probably about as complicated as it can get, which is why this is the last question in STAWA. So if you sort of got lost with this question, I wouldn't feel too bad. Okay, so those are 3 different specific heat calculations.